All right, welcome to this Chem 161 video, where we'll be looking at some Chapter 3 content, touching on properties of waves, and building towards the idea of a quantum model for the atom where electrons are in orbitals represented by a quantum representation for a three-dimensional wave. Okay, so let's first start with trying to understand some concepts for a wave. So we'll sketch a wave here with the vertical distance representing some amplitude and the x direction representing distance. And so we can extract a couple of metrics that are important here for characterizing this wave. The one might be the crest-to-crest distance. Okay, and if I had done a good drawing, this crest-to-crest distance is the same for this wave. And so we would call this the wavelength. And this gets the symbol lambda. So we have lambda as an important concept here, wavelength. And as we just said, it's a distance between two identical parts on this wave. Okay, so between two identical parts or features on the wave. Okay, so that is the wavelength determined by crest to crest is also equal to the wavelength determined by well to well, or if perhaps there was an origin kind of put right through the middle here, we could go through the midpoint or the intersection points with that axes represented by the dashed lines. So long as we're going to the exact same position, say for example here through to here, that distance there is also lambda. In this course, we'll be dealing with waves that mostly have wavelengths that are very small, and so we'll see a lot of measurements that are on the order of nanometers. So I'll remind you at this point that we have 1 nanometer, which is equal to a billionth of a meter. So that is 1 times 10 to the minus 9 meters. And sort of inverting this information, if you will, we also have that 1 meter is equal to 1 times 10 to the positive 9 nanometers. Okay, so again, wavelengths for light that we will be looking at for the colors of the rainbow typically are held within the range of 400 to 800 nanometers for the wavelength. Okay. Now also another metric we have for this wave is that this wave likely would be passing through this distance on our screen here over a certain amount of time. So we have the idea of frequency. Okay, so we'll put frequency next here. Frequency is given symbol nu. It looks like a tilted italics V, nu. And we'll have this as the number of wavelengths that pass a fixed point in a unit of time. All right, and so this is typically measured with the default units for time in seconds, many waves are very, very quick, so there's a high frequency. And so the idea is if this wave were traveling, and we picked a kind of crosshair point here on our origin, represented by the dashed line, that we would be looking for portions of the wave, this whole wavelength, to move past that point of interest and time it so that we knew the frequency. Okay, so you can see here the sentence would tell us that we would expect to be counting whole units of these wavelengths, so it's simply unitless in that regard per unit time. So this is going to give us units that are per second. 1/second is what we see for the units for frequency. This is also given a separate symbol, which is the hertz. So that is 1 per second is equal to 1 hertz, or 2 wavelengths passing a fixed point on a scale would be equivalent to 2 hertz. Okay, and an interesting property here about light is that the product of these two equals a constant. So the product of these two is equal and is defined as the speed of light. Okay, so we have speed of light and that's just like similar units to what you would have for you traveling in a vehicle or something, miles per hour. We'll use metric versions of that, so we'll typically see meters per second for those units. And the symbol used here is lowercase c. And we'll see that this lowercase c is a constant for the speed of light, and it is known to be 2.998 times 10 to the 8 meters per second. Okay, so this is a constant that we need to memorize for the speed of light. Okay, and as we just mentioned a moment ago, the product of the two former properties of a wave equal the speed of light. So that is, we have our first equation here that says the speed of light is equal to lambda times nu. Okay, so that is wavelength times frequency. Now, let's recall that the speed of light is going to have meters per second as its units. And so looking at the units here below, lambda should have meters. And if we input the per second for the frequency, we can see here that the units will work out. So when we use this equation, be sure that you are using wavelength in meters and using frequency in hertz or the per second value there. Okay, so let's take a look at a couple of examples and see what we can do with this. So we'll just make some room for that. So let's ask the question, what is the wavelength in nanometers, so we'll have to answer back in nanometers, of blue light, one of the colors from the rainbow, with a frequency of 6.4 times 10 to the power 14 hertz. Okay. So you can see the equation above might come in handy. We are given the frequency as 6.4 times 10 to the 14 hertz. So that is, we are given the nu value. We know C is a constant, so this is a one equation, one unknown approach. We need to determine lambda, so that is our approach. We'll use the given information that mu is equal to 6.4 times 10 to the power 14 I'll write it in the per second format there. And we also have memorized the speed of light to be 2.998 times 10 to the power of 8 meters per second. And so c is equal to lambda nu, and it follows therefore that lambda is equal to c divided by nu. And so inputting the parameters now, we're going to have 2.998 times 10 to the 8 meters per second divided by the frequency, 6.4 times 10 to the 14 per second. And to show you how units cancel, the per second in the numerator will cancel the per second in the denominator, and my only units left will be the meters. So this answer will come out to be in meters. And so we get about, doing this on our calculator, 2.998 double E8 divided by 6.4 E14. Here we get an answer that is 4.684375 times 10 to the power of minus 7 meters. And we were told to answer in nanometers, so we've only done one major piece of the problem. We now need to convert this into nanometers. So we'll follow up with a conversion by multiplying by 1 meter and having a numerator of a billion, so 1 times 10 to the power of 9 nanometers. There are 1 billion nanometers in a meter, and this will give us 468.4375 nanometers. And respecting sig figs, looks like we were given 2 sig figs here, so our answer should be written out as 2 sig figs. So the answer will be 470 nanometers for that answer. Okay, we'll try one more here quickly. Squeeze it in if we can. So here we'll go a little bit backwards. So we'll ask, what is the frequency of light having a wavelength of 681 nanometers. Okay, so maybe you want to pause the video at this point and try this one on your own and resume when you've had a chance to go all the way through. Okay, so we'll start by converting the wavelength information, 681 nanometers. We'll go into meters. That is a requirement for using our equation. So 1 meter has 1 times 10 to the 9 nanometers. So we're dividing by a billion, and so this makes this number 6.81 times 10 to the minus 7 meters. We recall our constant from above, the speed of light. C is equal to 2.998 times 10 to the 8 meters per second, which means we have 2 out of the 3 needed in our equation, and we can now solve for frequency. So frequency is equal to the speed of light divided by the wavelength. So this is going to be 2.998 times 10 to the 8 meters per second divided by the wavelength now in meters, as we've primed it a moment ago, 6.81 times 10 to the minus 7 meters. And this will give us the answer as 2.998 E8 divided by 6.81 double E 7 negative. And here we have 4.4023495 times 10 to the 14 per second, or hertz. And again, assuming 3 sig figs on the first one, we would report our answer to 3 sig figs, and so we would round at the 0 position. So the answer here would be 4.40 times 10 to the 14 hertz as an answer. Okay, so with that, we're now better equipped to know how to handle properties of light in the form of wave characteristics. And we'll see in the next little bit of discussion here on how the electron can be better modeled as a wave, given some things that we've learned about it from previous experiments, as we'll see. So join us for that next video, and